This is joint work with Magdi Belbasi, Antonio Blanca, Bob Harris, and David Kozlicki. So the talk is about sketching, which is a widely used technique in bioinformatics. It reduces the size of the data with the idea that downstream algorithms can now be faster and use less memory, and as a result, allows them to tackle bigger data sets. There are lots of sketching techniques in bioinformatics that I'm showing here, and there are lots of applications where it's used. But one of the problems with sketching is it has a potential to create problems with accuracy, and that's what I'll talk about today. The sketch I'll talk about is one of the, arguably the most used one in bioinformatics. It's called the minimizer sketch. I'll show with an example of a sequence here, ACGGAT. So the first thing we do is break this sequence up into its constituent k-mers. So here k equals 2, and we get AC, CG, GG, GA, and AT. Then we hash these k-mers to some number between 0 and 1. Okay. Then we take a window of k k-mers. So here, of W k-mers. So here W equals 2. We have 2 k-mers in our window, and we identify the k-mer that has the smallest hash value in the window. So here it's CG, and this is called the minimizer of the window, and we add it to the sketch. Then we shift the window to the right. We find the next k-mer with the minimum value, and we add it to the sketch. Now, sometimes the new minimizer is the same as the old minimizer, so we don't do anything. And here, finally, we add AT to the sketch. And so we have here the sketch of this sequence is the 3 k-mers CG, GG, and AT. So this sketch is, as I mentioned, widely used in sequence alignment, mapping, assembly, error correction, and so on. The thing we're going to focus on here is how it's used for mapping, in particular, how it's used to estimate the Jaccard similarity between 2 sequences. The Jaccard similarity is informally just the percent of k-mers that are shared. So here I'm showing a sequence A as before in terms of its k-mers, a sequence B, and an edge connects any 2 k-mers that are the same. So here the number of shared k-mers is 3, and the total number of distinct k-mers is 7. So there's 10 here minus the 3 that are duplicated. So the Jaccard here is 3 over 7, and gives us a sense of the similarity between the strings. Now, the Jaccard is simple to define, but computationally intensive to compute because you have to do this intersection between large sets of k-mers. So in reality, it's actually not often computed directly. What makes it nice is it's amenable to being used with a sketch. In particular, you can use it with the minimizer sketch I described. And what you do is you just take your minimizer sketch, compute the Jaccard similarity of the minimizer sketches, and use that as an estimator for the Jaccard between the full set of k-mers. And this is called the minimizer Jaccard estimator, or sometimes the WinNode Jaccard estimator, and we denote it here with J hat. Now, this is used in read mapping, and the idea is you have a read, you want to see if it maps to some location, you do a fast check of the Jaccard similarity, and if the estimator gives a low number, you discard this position and you move on. So the main question of the talk is, okay, what happens to the accuracy of your downstream process when you are using this estimator? So clearly, the estimator is a random variable because it depends on this random hash function. So it can't always give you the true Jaccard. So clearly, it's not going to be perfectly accurate. So how do we measure accuracy in this case? Now, statisticians have actually a very nice way to think about this. So even though at any given time you might get a different estimate, what you want is that on average, you get the true value. So more formally, the expected value of the estimator is the true value. And if your estimator has this property, it's said to be unbiased. Now, sometimes this doesn't hold, but a weaker condition holds. Namely, you might have a bias when the sketch size is small, but as you increase the sketch size, you decrease the bias more and more. So when this happens, the estimator is said to be consistent. Now, these are important properties for an estimator to have, because downstream algorithms, of course, they understand they're working with an estimate, so it's not exact. But you don't want the estimate to tilt one way or the other, because if it does that, it's going to result in bias of your results, which is probably not desirable for whatever downstream application you're using. A great example of an estimator that we use is the min-hash Jaccard estimator. So it's just like the Jaccard estimator for minimizers, except it's using a different sketch, the min-hash sketch. And the classical result shows that this estimator is unbiased, and that's really great. Now, what about the Winode or the minimizer Jaccard? Well, we looked at MashMap first to see if there's any evidence of bias in its output. And what we did is we simulated reads with a certain divergence, and we reported what divergence MashMap reported, averaged over many samples, over many simulations. And we see that there's a big bias in the output of MashMap compared to the true divergence. So now we look deeper into the estimator, the mathematical properties of the estimator itself. Why would it be biased? Now, the first intuition, which is actually quite incomplete, but it's a start, is that the Jaccard does not depend on the order of k-mers in your sequence. It's just, right, two sets and you measure the size of the intersection. But the estimator does depend on the order, because whether or not a k-mer makes it into a sketch depends on what other k-mers are nearby. Okay, so in this way, the order of the k-mers on the sequence does affect the estimator. Now, here's a concrete example where you have one sequence, which is just a permutation of the k-mers of the other sequence. So the Jaccard is just one, all the k-mers are shared, but the sketches are going to be different. I mean, they're not necessarily going to be the same in the upper and the lower sequence. So because the sketches are not always going to be the same, sometimes the estimator will give you a value less than 1, which means that if at most it gives you a value of 1, sometimes less than 1, in expectation it has to be less than 1. So in this case, we see that the estimator is biased. But that's actually not the whole intuition, because when we look at sequences like this, which the order does not change of k-mers, we still see a bias. So what's the intuition here? And I focus on the intuition because we won't have time to go through any of the proofs, even at a high level. So what's the intuition here? I would flip the question. Well, why do you think the Jaccard estimator should be unbiased? Well, that's the intuition I had initially. And my thinking was, well, if you have a higher Jaccard, that happens if you have more shared k-mers, which probabilistically means you'll have more shared minimizers, which means you'll have a higher Jaccard estimator. Okay? And this intuition is correct. But then when you think deeper about it, there's a lot of functions that may have this property. So the Jaccard is this particular function of the number of shared k-mers. And here I'm plotting it. Its y-axis is 0 to 1. And on the axis is the number of shared k-mers out of a maximum 100. And it's a function that looks like this. But there are lots of other functions that could have this property. These are two other examples of functions. Now, if your expected estimator behaves like one of these other functions, it's going to be biased, because for some value of shared k-mers, it's going to give you a different result than the true Jaccard. Now, you might still say, well, but the estimator and the true Jaccard have the same structure. They're both ratios. But this is really not enough, because what we show is that the expected value of the number of shared k-mers is not proportional to the number of shared k-mers. Okay, so let me now state the theoretical results. The first thing that's important to observe is that if we're to show that, considering only A and B, the two sequences, not having any duplicates each, if we show that there's bias in that scenario, it already shows that there's bias for the bigger family of sequences that do have duplicates. So it's enough for us to then consider to show bias in these duplicate-free cases. Now, I should say duplicate-free means A does not have any duplicates, B does not have any duplicates, but of course they can share they do share k-mers. So the first theorem tells us that the bias, this middle case here, is this middle term here, is sandwiched between, is basically equal to this term b plus minus this error term epsilon. Now the error term, important thing to note is that it goes to 0 as the length of the sequence goes to 0. Now the b, we have a closed form solution for it, but unfortunately there's like so much notation required just to write it down that I can't even show you that form, but it's easy to compute. So this basically says we've derived the formula for the bias up to a certain vanishing error. Now, the second theorem says that except for extreme cases, this bias is strictly negative. So it shows that the minimum Jaccard estimator is in fact biased. Now you could say, well, if you can compute the bias, why don't you just add it to your estimate and that will make the estimator unbiased? Now, unfortunately, to compute this term beta, I need the matching graph. And the whole point of doing a sketch is that you don't keep the original k-mers all, you just keep the sketch. So to compute the bias defeats the purpose here of doing the sketch in the first place. So next we wanted to look at a couple of concrete families of sequence pairs to see what that B actually is. So the first case we looked at here are what we're calling sparsely matched sequences. So in this sequences, the shared k-mer, the windows of shared k-mers never overlap. So these edges are never too close together. And this is kind of capturing unrelated sequences to some extent, because basically we're saying that, okay, you have these kind of, by chance, these edges here. Or at least they're not dense, they're spread out. So in this result, we show that we derive a closed form formula for B, which is just a function of W here. But when you plug in the numbers, what we get is actually, regardless of the window size, it's at most 63% of the Jaccard. So that's a bias of at least 37% that we see for this family. Now for the other extreme, we look at densely matched sequences. So here we imagine that the bottom sequence evolved from the top sequence by having a mutation every jth nucleotide, where J is just is large enough to be bigger than the window length. And remember, one nucleotide mutation actually destroys k k-mers. So here you see 2 k-mers destroyed, and so this kind of pattern would repeat here. For these types of sequences, we get a slightly more hairy formula for the B term, but it's still just an easy function to evaluate. But here it depends more on the numbers. So plugging in these numbers, for example, which are some things that MashMap would use, we get that the expected value of the estimator is about 10% smaller than Jaccard. Now, we wanted to look at to do experiments to see what this bias looks like on real sequences. So here I'm showing you the Jaccard, the true value of the Jaccard versus the estimator value. And this curve here, this is unrelated pairs. And here you see that the bias can be quite extreme. So for a Jaccard of 0.9, you might see, you see a bias, you see that the estimator is 0.4, so huge bias. Here for the related sequence curves, you see the bias is much smaller, but it's still substantial. So this kind of intuitively matches the theoretical results from before that kind of indicates or hints that in general sequences that are unrelated will have a bigger bias than sequences that are related. So in that spirit, these results agree. Next, we went back to the MashMap and we wanted to see, okay, is that bias that we see in the output of MashMap, is it due to the bias in the estimator, or is it due to, it could be whatever, right? It's a piece of software. So we found 2 causes of the bias in the output. The first is it uses an approximation for in the formula to compute the divergence from the Jaccard estimate. Okay, so that's a separate issue, and we could correct for this approximation by making it exact. And the second thing is the bias of the estimator, and we could correct for that too for these experiments just by replacing the estimator with the true Jaccard. And what we found is that correcting for those two things, we completely got rid of the bias in the output of MatchMap. If we look at here, for example, most of the bias was due to the estimator bias. There's, of course, more results, experimental results, and a lot more of the proofs and so on in the paper, but due to time, I won't be going into that. So here to summarize, we showed that the minimizer Jaccard estimator suffers from bias and inconsistency. On unrelated sequences, that bias can be drastic. On related sequences, it's smaller but still substantial. And this leads to downstream inaccuracies. This causes the accuracies of MatchMap divergence estimates being biased. So where does this leave the minimizer Jaccard estimator? Now, on one hand, you could say, well, maybe that bias is not so big, right? 1% versus 1.4% divergence. If I'm doing something like read mapping, it doesn't make a big difference maybe. And that's fine, and then you can keep on using it. Or you might say, okay, I'm doing fine-grained phylogeny reconstruction, and the difference between 1 and 1.4% is actually huge, and then you should probably use something else. I guess the take-home message is empirically test on the type of data you expect to understand what kind of bias you would expect. Of course, the easy solution is to switch to another sketch that is consistent and has similar properties to the minimizer sketch. For example, a recent paper, fragment hash, showed that this fragment hash sketch leads to an consistent estimator for the Jaccard. Overall, I think the bigger point I want to make with this talk is that we have to be more careful when we are looking at when we're using sketches. I think we all kind of jump on this ship because it gives us an easy way to scale up, but we want to do it in a controlled fashion. In particular, we don't want to have introduce bias in our downstream tools, or at least we need to be aware of that if that's what we're doing. And I'll stop here. Thank you.
Very nice talk, Paul. I'm very interested in this. The question I have, the whole thing I was thinking the whole time is, Jaccard in and of itself is somewhat a bad estimator of similarity, right? Like there's adversarial sequences where you can trip Jaccard. So my question is like, I almost wonder, is Jaccard or minimizer Jaccard here, is that almost better for remapping since it seems to downweight dissimilar sequences? So how
kind of two wrongs make a right. I mean that's a dangerous game to play.
Well, it was pushing down the dissimilar.
Yeah, it's pushing it in the right direction. It's actually pushing it in the direction you would prefer if it was pushing it in some direction. But I would argue that you kind of want to stay in control of what's happening as a developer. So yeah, maybe this is good in some cases, like it pushes it in one direction, but like if you want to estimate your false discovery rate or something like this, then all of a sudden you have no idea what's going on. So I would argue that you still want to try to make your estimator unbiased.
So that doesn't involve, since I'm a little weak here asking questions, but so did you test the similarity? So like the bias comparing Jaccard, regular Jaccard, and minimizing Jaccard with like edit distance? Yeah,
so that's I think there's a paper from Guillaume Mercier and Carl Kingsford and others that showed you guys showed like really like counter examples in both directions where the Jaccard can be showing you, like in this example.
I was gonna say, we just did like a very light.
Yeah, but no, we did not do experiments. But the question I would ask there is it a bias in a certain direction when you look at actual sequences? So that's if I was going to do an experiment, I would try to look at real data and see, okay, clearly there are like some examples where Jaccard similarity is really bad estimate of edit distance. Is that happening in real data? And if it's happening, is it biased in one way or the other? But no, we haven't done any of that.
Thanks.
Sure.